When we speak about derivative, we speak about change. For example, if we have a function like this and a value of the independent variable, let's say a. For this value of the variable, if this a is part of the domain of f, then we're going to have an image of a that in the graph define a point. So the image of a, it will be f of a. And this determine a point in the graph of f, and this point of course will be the value of x is a, the value of y will be f of a. So this will be the point a, f of a. If there is a change in a, let's see that the change is h, and then the value will be a new value that will be a plus the change in a, so it will be a plus h. And obviously this defines a new point in the graph, so we are going to have a new point in the graph, we're going to have a new image of the number, so that will be f of a plus h. That could be equal or could be different to the previous image. So f of a could be equal or different to f of a plus h. So we have now a new point in the graph of the function, and we can measure easily the change in the value of the function. First was f of a, now it's f of a plus h. So this measures the change in the value of the function. The change will be the last value minus the first value, so it will be f of a plus a minus f of a. And we have also a change on x, so we can measure the average rate of change of the function. And this average rate of change obviously is related to this line that passed through these 2 points, so the secant line that passed through these 2 points. And we know that the average rate of change of the function will be f of b, the value in the last value of x, minus the function evaluated in the first value of x divided by the second value minus the first value. So in this case will be f of a plus h minus f of a, this divided by h. So this is actually the slope. So the average rate of change is the slope of the secant line. So what we are going to analyze is what happens if this change in the variable x is different. So what happens, for example, if this h is smaller? And if this is h is smaller, the value a plus h will be different. And this value, the point in the graph will be different. We're going to have a new image, and this point will be different. So we have moved everything. Now we are thinking in another secant, and it will be the secant, the line that passed through these 2 points. So the rate of change if we move the point. So what we are going to analyze is what happened with this average rate of change. What happened even if the value of h is even smaller? If the value is smaller now we move everything, so now we have a new point, we have a new image, and the point is closer to the initial point, but now we notice that, and also we notice that the slope of this line will be different, so we have a different secant with a different line. So what derivatives do is think what happens if this h is so small that approaches to 0. So actually if this approaches to 0, then we're going to have a point that we're going to have a line that don't touch 2 points, but actually just 1 point. So we're going to have the tangent of this curve at that point. So the slope of the tangent line will be the limit as h approaches to 0 of the average rate of change of a plus h minus f of a over h. That is the value of b minus a plus h minus a is just h, so the value at the bottom. So that means that we have defined with this the instantaneous rate of change of f. So provided that this limited 6 is this limited 6, this limit defines the instantaneous rate of change of f. So it will be the slope of the tangent line will be the instantaneous rate of change, and we can compute it just computing the limit as h approaches to 0 of f of a plus a minus f of a over h. So f, the function evaluated in a plus h, minus the function evaluated in an initial point a divided by h. So the change in the variable x. So we have that the limit at h approaches to 0 of this expression is not only the slope of the function at that point, so the slope of the tangent line, but also is the instantaneous rate of change at that point A. That could happen for any point or for many points in the graph of f. So we can define a function for each value of x that is part of the domain of the function, but also for which this limit is 6. This function that assigned to each value in the domain of f, this limit, if this limit is 6, the instantaneous rate of change of f at that point is called the derivative of f. So the derivative of f is a function that assigned to each point in the graph of f, or for each value of x, the slope or the instantaneous rate of change at that point. So the slope of this line, if we have x, if x is this point, so the slope of this line will be the derivative at that point x. So the derivative will be equal in x, so the derivative at the point, at the value x of the independent variable will be the limit at h approaches to 0 of f of x plus a minus fx divided by a. And this gives me the slope of the tangent line at that point, or give me the instantaneous rate of change at that point, if that limit exists. A prime can also be denoted in several ways. You can use this symbol, y prime, or dy dx, which is the derivative of y respect to x, or this, the derivative of f of x respect to x. This notation, the y over the x, that just differentials here, is called the Leibniz notation and will be important in other topics. So we are going to be speaking about them later. Okay, so this is the derivative. In other videos I will be showing you how to use this definition of the derivative to compute instantaneous rate of change, or to compute the derivative of a function. So finding the derivative of a function using the definition. So this is the definition. So this formula gives me a definition of the derivative of a function. Wherever this limit is 6, there will be a tangent line, and this slope of this tangent line will be this limit. Thank you.